I'm not going to dwell too long on it because I want to give you a little time to work on your exercises. But this is from section 8.8, Taylor polynomial approximations. And this deals, it's this exercise here. And of course, Dr. Carbone is an engineer. Dr. Carbone, of course, if you have any insights, feel free to add in. And Dr. Carbone just made an announcement. He has his, as you know, WebAssign help session tonight from 8 to 9. So in this problem, a surveyor measures differences in elevation. This is from section 8.8. A surveyor measures differences in elevation when making plans for a highway across a desert. Corrections must be made for curvature of the earth. So they say if R is the radius of the earth and L is the length of the highway, show that the correction is given by this formula here. And then part B, once you have the formula, part B says use a Taylor polynomial to show that the polynomial approximation, and it would be of this, for this correction formula C, is equal to L squared over 2R plus 5L to the fourth over 24R cubed. Okay, and they are treating the correction formula, let's see here, I want to be a little bit careful. All right, well, that is the approximation formula. So how do they do this? I mean, you should see how they do it. So let me go right to the solution, and you can you know, have this in your, it's in your ebook. If you go to the solution, so I actually did myself work through how, I mean, I looked at their work and I understand how they get this correction formula C, and it's here in the recording. So if you want to study that part, you can always look at the video and do a pause. But you know, here's the road, right? The road goes along the earth, and it has this length L, and the earth's round, so there's your road. It's on the earth, surface of the earth. So even though the earth, the road like looks flat, it's a little bit round, right? Because it's on the surface of the earth. And the surveyor does his or her measurements and looks along this line here. But there is a correction that needs to be accounted for due to the curvature of the earth, and that's this correction C. And so they show how to get the correction C here in part A, but then in part B, they want to find that fourth degree Taylor polynomial for the correction C formula. So what they do is they say, well, we gotta then figure out the secant. We gotta find a Taylor polynomial or a Maclaurin polynomial for the secant. And so what they do is, it's a fourth degree Maclaurin polynomial for the secant. They take the first 4 derivatives. Let me switch over here. They take the first 4 derivatives and they generate a Maclaurin polynomial for the secant of x, and then simplify it here. But the x is, in this case, going to be theta. It's going to be theta, and they showed in part A that theta equals L divided by R. L is the length of the road, and R is the radius of the earth. Okay. And the way they come from this L equals R theta, incidentally, in part A, it's just based off of, like, if you think about circumference, right? Like the circumference of a circle. Circumference is equal to 2 pi times R, where R is the radius. Well, so 2 pi then is your angle, right, for a circle. A full circle, if you were to measure theta, your angle to generate a full circle, a full arc of a circle, theta is 2 pi. So if you're looking for the length of this road, Okay, it's just going to be the radius of the Earth times theta, where, you know, theta is here. Okay, so that should give you hopefully a little perspective into this formula, L equals R theta. But the x is theta, right? The x there, when we did our Maclaurin polynomial expansion for the secant of x, we recognize that that x is the theta. So what they do is, where you have your x in the formula for the fourth degree Taylor polynomial, they substitute in theta. But theta is, since L equals R times theta, theta is L over R. And that's how they get the formula here. You know, the circumference is approximately, no, the correction is approximately equal to R times the Maclaurin polynomial approximation for the secant of theta, which is 1 plus a half times quantity L over R squared plus 5/24 times the quantity L over R to the fourth power. And they reduce that, and that gets them this answer, okay, at the end. And so that's how they answer the part B. Okay, are there any questions up to, for part B? And I realize you know, might need to look at this a little bit more, but are there any questions? At least with the process. Okay, okay. Well then for part C of this question, they are asking, compare the corrections for the formulas in parts A and B. So in part A, right, you have the, let me just maybe use this little box guy here. Here's your, and let me maybe put it in blue. Okay, so let me do an erase here. Rectangle in blue. So here's your exact formula. And then here's your, in part A. And so that the box in part A is the exact formula for the correction due to the curvature of the Earth. And then in part B, the box there, that's your approximation to for your correction, your fourth degree Maclaurin polynomial approximation. And in part C, they want you to compare the corrections given by these two formulas here, because you want to see how good the formula is, right? You want to see how good it is. I mean, this is important. Engineers need to be exact, or sometimes bad things can happen, right, Dr. Carbone?
Yeah, that's exactly correct. And I just want to point out, you had to make that correction when we're looking at radar systems for low-flying aircraft. When radar systems are looking at low-flying aircraft, you have to take that into account, or you may not be detecting the aircraft. You may not be, or you may think you're being detected and not, if you don't take into account that curvature of the Earth.
You have to take in, okay, you have to take into account the curvature of the Earth.
Right. So this is, once again, it's the radar systems looking at low-flying aircraft.
Thank you, Dr. Carbone, for that insight. And Dr. Carbone, I may say this was one of your fields, right, that you worked in as an engineer. Am I correct on that?
You're correct.
Okay. All right. Excellent. Excellent. So for part C, what they do then, for L equals 100 kilometers and R equals 6,370 kilometers, which they tell you, you compute the exact answer. Let me see here. Let me put the rectangle. You compute the exact answer, which is here. And then you compute the approximate answer, which is, maybe I'll make this in red, which is in the red box. And you can see that this formula is pretty good. The difference between the two results is what, .000. Let me put this in maybe in purple. 0.00000000808 kilometers, which is 0.00008. I'm assuming that's times 10 to the 8th meters. Let me see here. I didn't even think about that part. Hold on. So Dr. Carbone, what I'm trying to do is establish here the, let me see here, going from, hold on, going from the kilometer measurement to the meter measurement. That's what I'm trying to establish here. And, you know, it should come to me easily. Kilometers, 1,000 meters, right? So, but I'm trying to understand how they're getting that meter measurement there. Let's see. Because see, if I were to give this problem on your final exam, that could be important, right? So, man, come on, rectangle. So I'm trying to go, okay, so let's see here. Oh, I see what they're doing. I see what they're doing. They're taking this 0.78500995736 kilometers, and I believe they're writing it as, well, what, you know, how are they getting to the box answer? Are they rounding? I guess they're rounding, right? You know, it's a little confusing for me to see what they're doing. Oh, I'm sorry. No. What they're doing is they're taking the difference. No, they're taking the difference, right, as I said before, between the exact measurement and the approximate measurement. And that's how they're getting this 0.000000000. Sorry, they're getting 0.00000000808 kilometers. But then they're going from kilometers to meters. Oh, okay. So what they're doing is they're multiplying this first measurement here in the box by 1,000, and that's how they get the second measurement here. Hold on, I want it in the box, right? That's how they're getting the second measurement. Students, are you comfortable with that? Are you comfortable? Maybe give me a thumbs up, at least if, I know you have to look at it more, but at least the process, are you comfortable with that? I'd put it this way, as the process, is it, do you at least sort of understand the details of what they're doing? If I can maybe have at least a 1 or 2 thumbs up, that would, I'll sleep a little better. Okay, thank you, Robin. Thank you. Great. So how many on this problem maybe wouldn't want to see it on the final exam, but say to themselves, wow, it's an interesting problem? Are there any thumbs up on that? Because I'm thinking of putting it on your final exam, but I think what I would do is, put it this way, if I were to put this applied problem on your final exam, how many would like maybe would appreciate maybe me letting you know ahead of time. Okay, we got a lot of. Okay, thank you. Wow, a lot of thumbs up on that, Dr. Carbone.
I noticed.
Okay, all right. If I put this problem on your final exam, I'll let you know. And again, you know, I'm sort of assuming that you would use this guide to help you answer the question. And and of course, I would let you know. How many think this is though a cool problem, a really interesting problem? I think it's amazing, a really cool problem. How many students think it's a nice problem, cool, a very interesting problem? Thank you, John. Okay, thank you, Darius. Thank you, Quentin, Tyreek. Wonderful. So, you know, I mean, of course, it makes my life a little easier, right, if I didn't discuss this problem. But then I don't feel I'd be preparing you for life, you know, as engineers and scientists. So that's why I wanted to do this one with you. Are there any questions on that? Okay, Dr. Carbone, do you have anything you'd like to add?
No, I think it's actually, not only is it an interesting problem, but it's an important problem. If you're doing anything in engineering that has to do with the any sorts of measurements that has to do with rotation, you know, with the Earth, you do have to take into account its curvature. And even if you have an aircraft flying at 30,000 feet, radars looking at it, if that aircraft is you know, say 100 miles away, you have to take into account the drop that you know, it's not at 30,000 feet relative to the position of the other, say relative to the radar that's say 100 kilometers away.
There's like a time delay or something.
No, it's not a time. It's actually the position. If the Earth is dropping and something, and you're 100,000, let's say you're 100 kilometers away, you know, you're at a certain point, right, on the Earth's surface. Now the other one is he's 100 kilometers away, but if he's 30,000 feet above the ground, he's actually dropped down, right? He's dropped because of the curvature of the Earth. So the absolute distance is not 30,000 feet. It's 30,000 feet minus some delta. Okay.
You have to account for the curvature of the Earth.
Right, exactly. And that's what you're doing here.
Wonderful, wonderful, wonderful. Well, students, do any of you have a question for Dr. Carbone relating to you know, what he just mentioned here? Okay. And all right. Well, how many found Dr. Carbone's insights helpful? Maybe give a thumbs up if you found his insights helpful. Thank you, Josiah. Thank you, Robin. Thank you, Francesca. Excellent, excellent. Thank you, Darius. Well, I think this is just a nice way to end this lesson. So let me stop the recording.